Hey kiddos, welcome back. I'm so glad to visit you again and teach you. We're still at Lincoln High School, coming to you from Forest Grove. So anyway, I'm super glad that we get to finish the year together. We are going to keep walking through physics and we are going to finish the curriculum. So we're going to do our last unit on quantum, nuclear, and particle physics. Just as a reminder, I will be continuing to communicate with you through the Google Classroom. So please, in the Google Classroom, set reminders. Go into settings and set a reminder for when I make posts and check the Google Classroom regularly. These lessons will be primarily videoed so that you can work at your own pace and then check in also on the Google Classroom. But I will be checking to make sure that you're engaged in the lessons and that you're continuing to work and grow. My only goal is for you to learn science, and let's finish the year and finish the IB curriculum as promised. Okay, so here's what I would like to do. It turns out that the typical program that I usually use to present my lessons has a really annoying watermark on the bottom when I'm not connected to a smartboard. So I'm going to go ahead and use OneNote so that I can write on my slides as I normally do. So happy Monday. I'll post a couple of lessons every week, and then again, you can work at your own pace. So today's goals are to intro topics 7 and 12. They're our last two topics. Collectively, we'll be studying atomic, nuclear, and particle physics. This is known as modern physics when studied together. We'll start quantum physics, which is in topic 12 first. So today we're going to be able to collect data to describe patterns in energy and frequency of light for Einstein's photoelectric effect. So what we'll be doing is kind of looking at light as a wave and seeing what evidence we're finding for different phenomena that light is acting like a wave. And then, is light acting like a particle? Maybe. And we'll start looking at what's called wave-particle duality of light. This is our last unit, so let's go ahead and dig in. I like to start this unit with a couple of quotes. They're kind of funny, they're kind of frightening, and they kind of give us permission to ask questions. So Niels Bohr and Richard Feynman are both quantum physicists looking at objects that are very, very small, particularly atoms. And Niels Bohr said, anyone not shocked by quantum mechanics has not yet understood it, which is saying that when we look at things very, very small at the atomic level, we don't have intuition about it. We don't experience quantum mechanics like we do regular mechanics. And so we don't have any intuition. And so the patterns that we see in quantum mechanics can be shocking and non-intuitive. And Richard Feynman said, no one understands quantum mechanics, said by a quantum physicist. So I feel kind of good about my B in quantum mechanics in college, if I'm being honest. All right. So let's first introduce quantum theory with maybe a phenomenon that you're familiar with. Maybe you've studied it in chemistry. So often an introduction to quantum theory is the atomic spectra. So maybe in chemistry, you look through diffraction gratings at an emission tube, right? A potential difference put across a specific element of gas. You excite those electrons in that gas and some light is emitted. And different elements produce light that's different colors. So we can't do that live here, but I have a spectral emission demo video attached to the Google Classroom, and I'd like you to look at it and remind yourself, what do those spectral emission lines look like for different elements? So the person doing the demo is looking through a diffraction grating, so a set of slits at a specific light. And I want you to think about, what evidence do you see in this demo for light acting as a wave? as a reminder, when light acts like a wave, or if anything acts like a wave, that thing reflects, refracts, diffracts, or interferes. So those are all evidence of something acting as a wave. Okay, so take a moment and pause. Watch that video. Okay, record some notes in the Google Classroom, and then we'll keep going. All right. So in the Google Classroom, you should have recorded what you saw and what evidence that light was acting like a wave. Hopefully what you saw was light diffracting, right? It bent as it went through those slits, and that's evidence that light is acting like a wave there. Okay. Now, a scientist named Balmer came up with a pattern specifically for hydrogen known as the Balmer series. It's a relationship looking at the wavelength of light. There's a constant that he came up with, and it relates to an integer. So for hydrogen, his equation is 1 over wavelength equals this capital R, which is a constant, times 1 over 4 minus 1 over n squared. Okay, where this n is an integer. Okay, and again, this is specifically for hydrogen, and right now we're not going to dig into the details, but what I do want you to know is that Balmer came up with this relationship to predict the specific wavelengths that would be produced in an emission spectrum in hydrogen. And he came up with this equation through guess and check. And so this was really just a lucky guess. Later on, we'll be able to derive this using a greater understanding of quantum theory. Okay, so now let's take a look at the photoelectric effect. So the photoelectric effect is something that's responsible for technologies like photovoltaic solar cells, solar panels, use the photoelectric effect. Our digital cameras use the photoelectric effect to produce a digital image. And this is the thing that primarily was responsible for Einstein winning his Nobel Prize in physics. A lot of people think it was his work with gravity, but really it was his photoelectric effect and his overall contribution to the study of physics. All right, so we're going to observe what happens when light hits a metal target. And that's what's happening in the photoelectric effect. So light from the sun or another source hits a metal target, and we're going to make some observations. And we want to ask ourselves, is this, what we're seeing, evidence that light is acting like a wave? So on the Google Classroom, I will post the PhET simulation that links you to the photoelectric effect. It's the PhET photoelectric effect simulation, and I have a link on the Google Classroom there. It is a Java applet, so those of you with Chrome-based devices won't be able to access it. I do suggest that maybe if you are able to access the photoelectric effect simulation, maybe you do a Google Meet or FaceTime or something with a group of friends. Find some study buddies, and you can do a screen share over Google Meet, for example, and do the lab together so that you can all have access to the simulation. I will also post a separate video where I manipulate the simulation without any commentary so that you can stop, rewind, pause, and take the data that's required. Okay, now in this simulation, they will give energy in electron volts and in joules. Okay. Actually in electron volts. And so I just want to remind you that 1 electron volt is another, electron volt is another unit of energy. So 1 electron volt is the amount of energy required to accelerate 1 electron or proton, right? Something that has the charge of an electron through 1 voltage, or 1 volt of potential difference. So 1 electron volt is the charge of an electron, the elementary charge, 1.6 times 10 to the minus 19 times 1 volt. So this times 1 is 1.6 times 10 to the minus 19. And 1 electron volt is that many joules. Okay. Right, how we got that again was 1.6 times 10 to the minus 19 coulombs, right, the charge of an electron, times 1 volt. So a coulomb times a volt is a joule. Right, so that's an important piece of information that we need for the simulation. Okay, before you open up the simulation, on the handout that's on the Google Classroom, this is where I'd like you to record your observations. Okay, and again, before you open it up, I do want you to, or start manipulating it, I want you to do some beginning observations. So do numbers 1 through 3 and the beginning observations before you begin to manipulate the simulation. Okay, so this is kind of what it looks like. So up here, there's a slider where you can change the intensity of the light, how bright it is. Down here, you can change the wavelength of light. Okay, this is an evacuated tube, right? You can visualize it as a glass jar. One side, we've got a metal target that the light is hitting on. The light hits that, and we might be able to liberate some electrons. And so on the simulation here, these little balls, these little dots, those are individual electrons that are coming off of the metal target. Okay? Down here at the bottom, if there's a current flowing, if some of those electrons hit the other end of the tube, you'll register some current, which is in amps down here in this yellow. Okay, and then here's a battery that's providing the potential difference in the circuit, and you can have no potential difference, or if you'd like to, you can take this slider and give the battery a negative or positive potential difference in volts. So as you do that, you'll see some graphs populate that you can use to take some data. So you want current versus voltage, current versus intensity, and here's energy in electron volts versus frequency. And this frequency, like if you had a reading of 1.5, that's 1.5 times 10 to the 15 hertz. Okay. All right, and then finally up here in this drop-down menu, you can change the metal target. So I will ask you to make observations as you change the intensity, change the voltage, and look at energy versus frequency for different metals. Okay, so when we're looking at the handout, when you're graphing your data, I do want you to graph, for number 5, the energy in joules. So please convert the electron volts from the simulation into joules using this 1 electron volt equals 1.6 times 10 to the minus 9 joules. I also want you to have frequency on the x-axis and energy on the y-axis. Please specifically find the value for the y-intercept and find the value for the slope. As a reminder,